Okay, so now we're going to talk about model selection and evaluation of models, and we're going to sort of kind of cover a broad range of topics under this umbrella. So we have a number of different ways we evaluate models in species distribution modeling. We also have some tools that I think are significantly underutilized in species distribution modeling, and I'm going to talk about some of those as well. So first off, I'm just going to tell you what I mean when I'm talking about model selection. I mean, I think often people just kind of think of information criterion-based methods when they hear that term, and that's not the whole field. I'm talking about essentially any tools we use to sort of decide between a set of candidate models. So we're going to talk about what that process is about, and then we're going to talk about how we do it and how, in my opinion, we've been doing it wrong. And then I'm just going to walk you through the very basics of discrimination accuracy, which is most of the statistics we use to evaluate models in this field, and then calibration, which I think is substantially underutilized. Then information criterion-based approaches. We're not going to go super deep into those, but I'm at least going to give you the idea. And then finally, I'm just going to talk a bit about visualization and how I think visualization is one of the easiest ways to select reasonable models, and one of the ways that we rely on far, far less than we actually should. First off, what is model selection? Now, as I mentioned, people often just think information criteria. That field is often referred to as model selection, but when I'm talking about model selection here, I'm talking about, in a larger sense, any criteria we use to decide which of a set of candidate models is going to be best for our purpose. All right? So in our case, that will mean we've got some occurrence points for a species. Here we've got a frog. And we've built some various correlative models that explain the distribution of that species in the context of some environmental gradients. And then we want to sort of compare those models and see which one does the best job of what we want our model to do. And that seems straightforward, but it's actually really quite challenging to select a good model. And there are conceptual reasons for that, which we'll get to in a little bit, in terms of like what you actually want your model to do and not do. But there's also issues that have to do with the data. So one of the kind of defining characteristics, to me at least, of niche modeling and distribution modeling is that we are dealing with data that is deeply problematic, and most of the methodological developments in this literature can be thought of in the context of we're dealing with these problems with the data in one sense or another. So people often use kind of Venn diagrams and things like that, like the BAM diagram and stuff, to sort of talk about this, but I think that sometimes runs a risk of looking too clean and too pretty. And so I want to show you, based on a simulation, what your data actually looks like in the real world compared to what you're trying to estimate. All right, so here's a simulated fundamental niche of a species in the context of two environmental variables. So here we've got a little frog, we can say, again. So brightly colored areas, or combinations of environments, are combinations of environments that are good for our species. It's happy here. And dark colored areas are combinations of environments that are bad for our species, right? So this is actually what we often want to know. Not always, and I'll talk about that later, but often this is the thing we're trying to estimate. So this is essentially the fundamental niche of these species with respect to these two variables within these bounds. And this is what we want to know if we're going to, say, predict the suitability of habitat for our species across Australia, where it lives. But there's a lot of issues here. So first off, our species doesn't live in environment space, right? Our species lives in Australia. And that's already a really big issue. It's not an easy one to see, but the thing is, every grid cell in Australia has a temperature, a precipitation, and what have you. And so every grid cell in Australia can be mapped to some grid cell in this environment space. But the converse is not true. There could be combinations of these two predictor variables, which could be good for our species or bad for our species. So, for instance, here, this combination of variables is pretty good for our species. So there could be suitable combinations of variables that don't occur anywhere in Australia. And in fact, when you take what is available in Australia and map it into that environment space, you get this. So now these white areas are combinations of these two variables that don't exist anywhere in the continent of Australia. And that's actually a really big issue because it means we've got this combination of environments that's actually really suitable for our species. And if we monitor every single square meter of Australia and every individual of our species, we will never see them in this combination of environments because there's nowhere where they can access that combination of environments. Similarly, when we go to sample background data or absence data or pseudo-absence data, there are combinations of environments that we can't even sample for background or pseudo-absence data because those combinations of environments don't exist. There's nowhere like this for us to not find them in. It's a strange way to put it. There's nowhere like this for them to not be. But what that means is there are regions of environment space, and you sort of eyeball this, it's about half the environment space, where we cannot get presence data, we cannot get background data, we cannot get absence data. We got nothing in these areas of environment space, and yet, if we're talking about predicting the effects of climate change or the ability of our species to spread to another continent or whatever, we may actually be making predictions in these areas of space where not only do we not have any presence data, we don't even have pseudo-absence data. So that's a big issue. But that's just the start of it because our species is not dispersing all the way across Australia. It's a little frog, right? And so it's got a limited range. It lives down here. And because of that, what it can actually access in any given generation, the habitats it's sampling from, are going to be restricted to those that it could actually disperse to. And so the environment space it actually experiences, good or bad, is here. So if we want to make a prediction across all of Australia, we're down to only having about 10% of the combinations of environmental variables that occur across Australia even available to our species. And then we've got spatial sampling bias, and that sort of knocks our species, the probability of observing our species, out of whack with respect to the true suitability of habitat, right? So we've got a biased subset of a biased subset of a biased subset of the environments we're trying to make inferences about. So in a case where we actually want to estimate this fundamental niche, we've got a real problem in that we have got a bunch of other phenomena between us and it. Right? So our data is up here, and it is affected by all these processes. And if we wanted to estimate the fundamental niche, we've got to try to figure out how to factor these other processes out. We've got to try to essentially see through this stack of interacting processes to get just this particular nice little thing underneath. This isn't always the goal, estimating the fundamental niche, but I'm just saying, I'm using this as an example where we have to see all the way through all these things, right? And that's going to be challenging. Our data is really affected by a whole bunch of processes that have nothing to do with the process we're trying to estimate, or not a lot to do with the process we're trying to estimate, and we have to try to factor all these other processes out in some cases to get the answer we want to get. And so we're never going to be really great at that, quite possibly. You know? I mean, there's just fundamental shortcomings in the data that limit our ability to infer the thing we want to infer. And it's really easy to get kind of depressed about that. But I would recommend keeping this in the quote in mind. You've probably seen this before. It's by George Box. It's all models are wrong, but some are useful. And it's a cliche at this point. You see it in almost every modeling talk. But it's one of those things where it's a cliche because it's actually really good. You know, it's a cliche because it's so true for so many undertakings so much of the time. And it's also really important to keep in mind. So I've just sort of said this part here. All of our models, all of our niche estimates are always going to be wrong to some extent because the data is representing a bunch of processes that we actually don't want in many cases to show up in our model. So we're trying to get rid of those processes and we're never going to be perfect at it. But this part is just as important to remember. So all our models are going to be wrong, but some models are going to be useful. So if we can't see that fundamental niche, maybe we can at least see enough of it that, let's say you're a stakeholder who's trying to make a conservation decision or something like that, maybe you can see enough of the fundamental niche that if you incorporate that model into your decision-making process, you make decisions that make the world a better place. It's okay if the model's not right about everything, as long as it's right about the important things. So, I think that's important to keep in mind. Don't get too depressed about the fact that our data sucks for what we want to do with it. Think instead about how to make sure that the model you're making is useful for the thing you want to make it for. I do have a corollary to this statement, though. It's that some models are wrong and useless. So I think it's pretty easy to fall into this trap where you say, okay, I've built a model that can predict the effects of climate change on this species. Therefore, I've built a useful model. But the thing is, if that model is very wrong about the effects of climate change for that species in the conditions you're projecting it to, you might actually make worse decisions by incorporating that model into your decision-making process than you would make by, say, just using a range map of the species' current distribution. So it's possible to make models that are wrong, and if you apply them to decision making, they are so misinformative or uninformative that you actually make worse decisions. So if we want to really kind of sleep at night and justify our existence, we really need to know when we're making a wrong model that's useful versus a wrong model that's useless. We want to have some idea that our model is making a prediction in the world that we can rely on enough to improve our decision making, or if we're doing sort of more basic science, to improve our understanding of the natural world. So how do we pick a useful model? This is, I think, it's one of those questions that initially seems very simple, but it gets deeper the longer you look at it, and you just, I think, eventually come to the point, as I have, where I think this may be the most important question in this literature that we don't have a very good answer for. So Rob, in his sort of overview, I think I got this quote right, said, over and over the past 20-odd years, we've realized that many of the things we used to do aren't very good. And that is very true. I would add the things we do now probably aren't very good either, but we hope they're better. And I think we can get significantly better still. But getting better at this requires us to think harder about it than we're used to thinking at present. So we need to start from the basics. What does a good niche model or distribution model do? What is it that is the defining characteristic of a model that is good for your application? Is it enough that it fits your training and test occurrences, however you set aside test occurrences? Is that enough? Or do you want to be able to predict new occurrences that don't occur in either of those data sets? Or do you want to predict the relative suitability of habitat? So make a quantitative estimate. This habitat is not just better than that other habitat, it's twice as good, or 1.78 times as good as that other piece of land. Is feature selection important for our question? Do we actually want to know which predictors are most relevant to our species? Do we want to get biologically meaningful parameter estimates for the species' responses to those environmental gradients? Do we want to extrapolate to new conditions? Do we want to control model complexity so that we're keeping things as simple as we can and observing sort of scientific parsimony? So all of these are things that in some conditions you might want or need out of a model for a given application. But one of the things, we're going to dive deep into this in a second, but one of the things we're really that's really problematic about this is that these may trade off against each other. It's possible that if you want your model to do this right, you basically can't do that right. If you want your model to do this right, maybe you can't do that right. So it's really important, I think, in any given undertaking to start with, what do I want this model to do? What actual values, numerical values, am I taking out of it? What is it most important that it be correct about? And we'll dive into why that's so important in just a second. So model selection, broadly speaking, can be seen as managing compromises between those objectives. It's unlikely that any given model is going to maximize all of those at once, and as a result, you need to be clear on what the most important aspects of performance are and evaluate your models appropriately. One of the issues there, though, is that some of those things cannot be directly measured for real species. So if we're talking about, for instance, feature selection, figuring out which predictors are most important to your species, in many cases, you can't really validate your model against, say, physiological experiments that would tell you whether it's max temperature or mean temperature that's actually driving stuff. So in many cases, we're kind of basing our model selection on an assumption or a sort of formalized hope that evaluating on the things that we can observe is actually related to our model's performance on the things we can observe. That assumption can be quite problematic, again, as I'll show you in a minute. So that's what we want to do. We have all these different aspects of model performance. We want to select a model that optimizes the aspects of performance that we need for a specific decision or empirical study. So then what do we actually do as opposed to what we should do or what we want to do? And primarily what we do is we use a thing called discrimination accuracy. So discrimination is, it's probably most of the time when you think about model evaluation and species distribution modeling or niche modeling, this is what you're thinking of. It's everything like AUC and TSS and kappa, training and test data, you know, however you partition your data, whatever. Mostly what we're evaluating in this field is discrimination accuracy. And the way that works is we just have occurrences for a species. We build our model, and then we basically just ask, how well does that model distinguish distinguish between places where we know our species has been observed and places where it has not been observed. So we're going to collapse this down to like a one-dimensional environmental gradient here and say, we've got a bunch of occurrence points at one end of this one-dimensional environmental gradient, and a bunch of absence or pseudo-absence or background points at the other end of this gradient. And so discrimination accuracy is just saying, how well does my model assign higher scores to my known presences than it does to my known absences or background data or whatever. And so this here is now a model with a great discrimination accuracy, right? Higher scores for all your presences than for all your background points or absences. So there's a threshold you can draw here above which are all your presence points and below which are all your background or pseudo-absence or absence points. So that makes sense, right? And this is basically what, you know, AUC, TSS, kappa are just different flavors of this. But then by many metrics, this also has perfect discrimination accuracy. So even though this model is predicting quite different responses in terms of the continuous habitat suitability, there's still a threshold you could draw, above which you've got all your presence points and below which you've got all your non-presence points. So this has perfect discrimination accuracy by many metrics, and so does this. And in fact, with this data, if you're willing to allow your models to be arbitrarily complex, you can make an arbitrarily large number of models that all have great discrimination accuracy. And there are two things you can take from this little toy example, both of which I think are pretty important. One of those things is, okay, so we've got great, in fact, perfect discrimination accuracy for a whole family of models here. And some of these seem biologically realistic, possibly, and some of them seem a little crazy. If you interpret that as a species' physiological response to an environmental gradient, it's hard to make very much sense out of it. So that implies that discrimination accuracy might not be that great for saying which models are biologically plausible, if we like to think of them as representing some underlying mechanism. So that's one way of looking at this. Another way of looking at this is, okay, all these models, it's not just that they have good discrimination accuracy. It's not even, the problem isn't just that they have perfect discrimination accuracy. The problem is they have the same discrimination accuracy by many metrics. Meaning, these models aren't just all good, they are indistinguishable by discrimination accuracy. So there can be a very loose mapping between a certain discrimination score and what the internal structure of your model actually looks like. So if what you care about is something like this, is whether or not these responses are biologically plausible. Discrimination accuracy might not have that much signal. And we can see that with real species distribution models too, right? We can take our simulated data for our little frog, we can build models using a bunch of different methods, and we can get very similar predictions of habitat suitability. So we get very similar levels of discrimination accuracy for these different models. And yet, when you map these models into that two-dimensional environment space, they look wildly different. So you can make very similar geographic predictions based on wildly different underlying niche estimates. So, that's a bit of an issue, right? If you really care about these things as biological estimates, this is saying discrimination accuracy might be, at best, fairly noisy. And we'll dig more into that in just a minute. So there's another way to evaluate models with this sort of data, and it's starting to gain a little bit of traction. So Phillips and Elith had a paper out about calibration with some specific extensions for species distribution modeling. Yeah, I don't remember how long ago that was. 6 years ago, 7 years, I don't know. Anyway, but this is things like continuous Boyce index and maximum calibration error or expected calibration error, things like that. So calibration is fundamentally different from discrimination in a way. It's one of these things that seems like a subtle detail until you see how they actually work. And it's like, oh, actually, yeah, that's actually quite a different thing. So what calibration is doing is it's taking these continuous suitability scores and it's actually saying, what if we treat those as probabilistic estimates? If we treat these as probabilistic estimates, are they actually, based on a given data set, making accurate probabilistic statements about where I observe my species? So what we can do here, for instance, is we can essentially, let's say we take the most suitable grid cell in the entire map. And then we take the second most suitable and the third most suitable, and we collect up grid cells until we have a collection of grid cells that has an average probability of 0.9. Now, if these are accurate probabilistic estimates, then when we go out and observe a whole bunch of new data, 90% of those grid cells should be occupied. But in this case, they actually aren't. Right? And then we can take the next X number of grid cells until we get the next bin down that has an average probability of 0.8. And we can essentially just work our way across the landscape and say, binning up our grid cells by suitability, how correlated is the predicted frequency that we should observe our species under those conditions versus the observed frequency which we observe our species under a set of conditions. And so there's various metrics that measure essentially how well your predicted probability of presence matches your observed frequency of presence in an independent data set. And so this is basically what calibration is doing. It's not saying just, do we assign higher scores over here than we do over there? It's actually asking, how close are we falling basically to this line where our predicted and observed frequencies equal each other? So those are two very different aspects of model performance, but you might ask yourself, can I pick a well-calibrated model with discrimination accuracy? If I want those probabilistic estimates to be relatively accurate, if I want to say something about the relative suitability of habitat for my species, I mean, again, one of those quantitative differences, not just, oh, they're likely to live over here and not likely to live over there. If you want to say this habitat is, you know, X% better than that habitat, if you want that, that's calibration. Can you actually pick well-calibrated models using discrimination accuracy? So I had a paper that just came out last year. It was me and Nick Matsky and Teresa Iglesias, where we didn't actually measure calibration directly. This is a simulation study, so we could actually measure the correlation between the model and the true suitability of habitat, which is actually a little more precise than calibration, but it's very closely related. So we asked whether a model that has good discrimination accuracy is actually good at making continuous estimates of habitat suitability. Right? So again, this is not quite the same as calibration, but it's very close, should be very related. So We did simulations exactly like the ones I just showed you, and we built models using a bunch of different algorithms. And since this is simulated data, we could actually ask, how well does the true suitability of habitat match our model? And also, how well does our model predict our species' current spatial distribution? So we're calling this functional accuracy, which is, again, close to calibration, but not quite. And then this is discrimination accuracy. So basically, we just want to know if you could pick models that do this well by picking models that do this well. And the answer is, under most simulation conditions, those two things are not related usefully. So here we've got test AUC, but we also did this with TSS, we did this with kappa. On the y-axis, we've got how correlated is the estimated suitability of habitat with the true suitability of habitat. And then we've got these 7 different algorithms here. And what you can see is that you just straight up cannot, under these simulation conditions, and then I'm going to put an asterisk there that we'll come back to, you cannot pick a model with good discrimination accuracy and assume that that's a model that actually estimates the relative suitability of habitat usefully. This is based on, what is it? It's like a 1,500 models for 300 simulated species, or I don't know. It's a large study. It took months to run. That's a problem, because it says that discrimination accuracy, regardless of which discrimination metric you like, is a poor predictor of which models accurately estimate the relative quantitative suitability of habitat. I said, I put an asterisk for like under these simulation conditions, right? And I want to get to what I mean by that. So those simulation conditions were, we used all 19 bioclim variables and the default settings for those different algorithms. We varied the background size. We did spatially structured test data versus random test data. None of that made a difference, or not a huge difference, actually. Spatially structured test data did perform better than randomly withheld data, but still, discrimination accuracy was not a great predictor, even under those conditions. The one set of conditions where we found discrimination accuracy was arguably a usable predictor of calibration or the ability to predict habitat suitability was when models are kept very simple, so 3 to 4 predictors maximum, and the functional responses you're fitting are biologically realistic. So this means if you think if the true response of the species to, say, temperature is a smooth curve, you should be fitting a smooth curve to that if you want to use discrimination accuracy to predict or to select well-calibrated models. So, and to be clear, this basically is the 3 to 4 predictors. We used a sample size of about 100 data points, with 70% for model construction and 30% for evaluation. So 70-30 split. And we found that you could do, 3 to 4 predictors max. The number of predictors I expect, the number of predictors that you could get away with and still use discrimination accuracy to select well-calibrated models, I believe that would probably go up if you had a larger sample size. We did not evaluate that. That would be a really cool future study. But this is kind of saying, in my mind, if you are, have 100 data points or fewer, and you're trying to build a model where you can trust the relative suitability of habitat, those continuous suitability scores, using discrimination accuracy, you really actually shouldn't trust your model selection there for that purpose unless you're using a very small set of predictors. So, 3 to 4 predictors, and also thinking pretty hard about what those functional responses are like. And to be clear, it's easy to interpret this as saying more complex models are inherently bad or making unreliable predictions. That's not actually what this means. This means not that the models are bad when they're more complex. It means as models get more complex, we have a harder time telling good models from bad. Your model selection, if you're using discrimination accuracy, gets more and more noisy with respect to your actual modeling goals. Does it matter that we can't select well-calibrated models or models that get the continuous suitability of habitat, that we can't select them very effectively using discrimination accuracy? The answer is that it actually depends very much on what you want your model to do. Like if you are basically building a model to say, I'm going to go out under these current conditions and sample some frogs tomorrow, I want to know where to go look. Actually, discrimination accuracy is what you want. It says, yes, it's there versus no, it's not. And, maybe you don't care about the continuous suitability of habitat. You just want to go catch a frog, and then that's fine. That maybe those suitability scores are more noise than signal. But there's a whole bunch of applications that we use these models for where the continuous suitability scores are actually crucially important. So we use these models quite often, and we measure things like niche breadth on them, right? So this is one of those Levin's niche breadth metrics. 1 over sum of squared probabilities, basically. So, yeah. Or this is the expected frequency of observing it in a particular habitat patch. But that is essentially the same thing. Which means if we want these niche breadth metrics to be accurate, we need well-calibrated models, not models with good discrimination accuracy. Similarly, our metrics of niche overlap that we use in all these tests and E&M tools and things like that. If you look in here, whoops, yeah, those are probabilities or relative frequencies, which are effectively the same thing, which means that our niche overlap metrics are essentially meaningful to the extent that our models are well calibrated, or at least proportional to a well calibrated model. And a lot of people like to stack up the suitability scores and use those to essentially make an estimate of species richness based on that Poisson binomial distribution. But the use of these models in that context actually assumes that these are, again, probabilities. And so even this idea of stacking up continuous suitability scores to estimate relative species richness is contingent on the assumption that these are well-calibrated models. So for some applications, you just want discrimination accuracy, and that's cool. But for many applications, like the metrics we use only work if model predictions can be treated as probabilities, which means those models have to be well calibrated. And what I've just shown you is that in many conditions, discrimination accuracy cannot tell you which models do that. So we may be selecting models in many cases based on criteria that are unrelated to the performance we want under the conditions under which we built those models. That is a clear problem. And this problem may extend well beyond any given empirical study, because we've also got this whole literature of, methodological choices we make, which algorithms work best, how we choose our study area, what sample size we need, and all that sort of stuff, which is almost entirely driven by discrimination accuracy on randomly withheld subsets of your data. And it's entirely possible that for applications where we want well-calibrated models that make, reliable probabilistic estimates, every one of these methodological choices could be entirely wrong. So we need to really reevaluate that. And let's think for a minute, under what conditions do we need a model with good discrimination accuracy versus the one that is well calibrated? And under what conditions are we trying to see at which, like these different sort of levels of the processes that generate our data? I said that in kind of a weird way, but you'll understand what I meant in a second. So we've got a fundamental niche. We've got all these other processes that we talked about, what habitat's available in the real world, where are species' actual ranges, spatial sampling bias, biotic interactions, all that sort of stuff. But it's worth thinking in any sort of empirical study, what aspects of this do I want parameterized in the model versus factored out of the model to the extent that I'm able? Do I want to drill all the way down to the fundamental niche, or do I just want to actually estimate where my next occurrence point is coming from? So like, for instance, if you had, for some reason, a question, like let's say you had a citizen science data set, and you wanted to ask, where is my next point likely to come from? The next time someone whips out their cell phone and takes a picture of this mushroom, where are they likely to be standing? Well, in that case, you want all the biology, but you also want spatial sampling bias. And so you want a model that just does prediction and parameterizes essentially all these other phenomena in there. Contrast that with the question, where are we likely to see our next data point if we did unbiased sampling? Well, in that case, you're actually kind of trying to see through the spatial sampling bias and estimate, essentially the continuous suitability of habitat in the species range. You could ask what your species' geographic range is likely to be. And in that case, you're actually asking a question that's more like discrimination accuracy, but within the species' native range, as contrasted with the continuous suitability of habitat within the species' native range. But think about these things in terms of model selection. If your goal is to do this, you might want to use discrimination accuracy to select your best model. If your goal is this, you might want to use calibration, right? So it's worth thinking about what quantities you're actually extracting from these models and what has to be right for you to get the right answer. You could say, what is the potential range of our species? In which case you're talking about discrimination accuracy, but you actually want to go deeper than, you want to factor out dispersal and all that sort of stuff. You want to make a prediction at the continental scale, but then you want to actually, your ultimate value you're extracting is binary, and so you might want to use discrimination accuracy. Versus, again, relative suitability of habitat at the continental scale, you probably want to use calibration. And if you want to dig all the way down to the fundamental niche, it's possible none of those things will actually do a great job of that, but ultimately you're probably going to want something calibration-ish, and possibly even some batter metrics that actually work in environment space. And Russell Dinage and Mariana Simoes and Linda Beaumont and John Baumgartner and I are all sort of working on something that does some of that. So I'm not saying what I've given you is the definitive answer for any of those applications even, but hopefully I've impressed you with the fact that you actually need to think before you start building models even of how you're going to evaluate them. And the answer shouldn't necessarily be automatically, I'm going to do test AUC on randomly withheld data or spatially structured data. It shouldn't be a one-size-fits-all solution. It should actually be tailored to the values that you're extracting from your predictions. All right, so now we're going to skip to possibly the only aspect of this they really wanted me to talk about. I wasn't sure what they meant by model selection. I'm giving you the whole thing, but at the very least, they definitely did want me to talk about this. Information criteria. So this is still a little bit fringe in niche modeling and distribution modeling, but is increasingly popular, I would say. So let's go back to this example we had here. I said some of these seem biologically more plausible than others, and essentially that was just an intuitive argument based on complexity. But I think most of you probably just kind of nodded along with that, because we do have this intuitive feeling that these species' physiological responses to an environmental gradient, if that's what we're actually trying to measure, that those should be relatively simple. So, in our example, all of these had the same fit, but what if they had different fits? What if this fits the data better than that one? Is this a good model or is that a good model? This is essentially what information criteria kind of try to do. And the basic underlying idea is that there is some underlying process or set of processes that generate, let's say, the probability of a species occurring under a given set of conditions along some hypothetical gradient. So this is the truth that we're trying to estimate. So what we're essentially doing with information criteria is we're saying when we build a model to estimate that truth, it's not going to fit the truth perfectly. There's going to be some loss of information based on us effectively simplifying the truth to make and parameterize a model. Right? So these are all the places where our model fails to fit the truth. If we make a more complex model, we might get a better fit to the truth, where we're sort of losing less information, but we've added a parameter. And of course, we add enough parameters, we can fit the truth, if we had the truth to parameterize with, perfectly. All right, well, that's conceptually relatively simple. It gets a little more complicated because we actually don't have this truth function. We don't know what that looks like. We know what the data looks like, right? We have no truths, only data. So we can't measure how well a specific model fits the truth, but we can measure how well it fits the data. We can say when we use this model to approximate our data, how well or how badly does it fit? How much information are we losing about our dots positions on the y-point by using this y-axis, by using this model and the occurrences on the x-axis? And so we can measure that, and we can measure this. And the thing is, the difference between how well this model fits the data and how well that model fits the data should be very tightly related to how well those two models fit the truth that generated that data, right? So we're using the data kind of as an approximation of the truth, and then we're measuring the information lost when we use a model to approximate that data. So this is the main information criterion I'm going to talk about. There's this small sample size corrected version. There's a Bayesian information criterion. There's a bunch of different flavors of information criteria, but they're all essentially doing some flavor of the same thing. And AIC is very simple, so we're just going to stick with AIC. So AIC is just this: 2k, where k is the number of parameters in your model, minus 2 times the log likelihood. So first off, we're going to focus in on that log likelihood. With respect to a species distribution model, the way we get this is we take this model and we standardize it so that all the grid cells suitabilities put together sum to 1. So that essentially makes this a probability distribution over this geographic space. And then we extract the probability at everywhere we've observed our species, and we can multiply those together to get the joint probability of observing our data given this species distribution model or niche model. And that probability of our data given our model is proportional to our likelihood. It's just a likelihood times likelihood is just that times a constant. So this is how we calculate likelihood. Hooray. We typically actually don't multiply a whole bunch of probabilities, though, because that means that this product gets very, very small. Since all these are less than 1, you keep multiplying a whole bunch of, 1,000 probabilities together, you're going to get something very tiny here. So we tend to actually add the logs of them together, which is the same as multiplying them. So we add those logs together, we get the log likelihood, and that's essentially the same operation, but is less likely to run up against the precision limits of what you can actually store in a computer. So that's what goes in here. And then this k here, this actually just comes straight out of our model. So here we fit a quadratic model. So we've got an intercept, we've got a linear term, we've got a quadratic term. So k here would be equal to 3. So it's worth sitting down and having a look at this for a second and thinking about, okay, what happens? We're controlling our model fit. We're controlling our model number of parameters. So just look at this equation and think, what happens as this model fits better? Well, if the model fits better, all these likelihoods, or at least some of these likelihoods, will go up, which means this log likelihood will go up, which means that this 2 log likelihood will go up. But we've got a minus sign here. So as this gets bigger, as our model fits better, our AIC goes down. Right? And then you look at this 2k here. What happens here is our model gets more complex. As our model gets more complex, we get more parameters that we're estimating, which means k goes up, which means a more complex model will increase AIC, and a simpler model will decrease AIC. So, if a simple model fits well, our AIC would be very low. If a model fits well, but is very complex, our AIC will be somewhat higher. If our model fits poorly and is very complex, our AIC will be very high indeed. So basically, this is a metric that goes up as models fit poorly and up as models are more complex. And it goes down as models fit well and down as models become simple. So what AIC really wants is a simple model that fits well. All right, so let's discuss a few things that you should probably know about AIC if you're going to use it. The first is it wasn't developed for Maxent. It's been around for a long time. I think its first use in Maxent was my paper with Steph Seifert from 2011. AIC is pretty uncontroversial when used with GLMs and GAMs. So that's nice and straightforward. It's still somewhat controversial for Maxent models, and there's good reasons for that, and I'll get to those in just a minute. One thing I think is worth pointing out is that you can actually use AIC to compare your species distribution model to a null model, and it's not something I'm sure I've ever seen anyone do. All you actually have to do is basically generate a model that has the same value in every grid cell in the study area. And then once that is basically standardized so it all sums to 1, that basically approximates an intercept-only model of the species distribution, which is essentially what we use as a null model for AIC model selection in other contexts. So you actually could build a model or a set of candidate models, but include in there a null model and quantify at the very least how much better your model does than no model at all. Not a huge innovation, but something that seems doable that I've never seen done. A couple of things worth knowing. There is no absolute scale for AIC. It's not a metric where there's, a perfect model has a score of 0 or something, right? Unfortunately, we just don't have that ability. But it's actually AIC values, they only make sense when compared to other AIC values, but it's actually even more restrictive than that. AIC values have to be compared to other AIC values that were calculated using the exact same data points. You cannot use AIC on one set of data points and compare it to an AIC that was calculated on another set of occurrences. It just fundamentally does not make sense. So don't do that. I've seen that happen a few times when reviewing papers, and just don't do it. The way AIC is traditionally calculated would be analogous to only using training data in a species distribution modeling framework. So you calculate your AIC on your training data with no data withheld for testing. I'm not saying it's not okay to withhold data for testing and then you use your AIC on your training data, just that's somewhat inconsistent with classical applications of AIC. And that's not just a technical detail. It's not just that people didn't think of withholding test data for AIC. There's actually this deep philosophical divide. I don't know that people are really arguing about which side is correct, but there is a deep split in the philosophy of modeling that AIC comes from versus a machine learning framework that Maxent is more typical of. So the sort of AIC kind of comes from more classic statistical modeling literature where we're concerned about overparameterization and getting precise parameter estimates and all that sort of stuff. Maxent kind of comes out of machine learning literature, which more or less focuses on prediction over and above estimating some underlying true process, right? And so it's worth knowing that when you're using AIC on Maxent, you're essentially stepping across not just some statistical boundary, but in fact a philosophical one. That said, there are some real similarities there between what AIC does and what Maxent already does. So let's just look at what Maxent does. This is from Phillips and Dudick 2008. Maxent can be thought of as maximizing this, which looks a bit hairy as an equation is concerned, but as far as an equation is concerned, but this is actually just the log likelihood, right? And this is a term that penalizes for the number of parameters. What does that look like? Well, that looks a whole lot like AIC, just kind of rearranged, right? So this log likelihood, this is what's over here. And this penalty for number of parameters, it's a different formulation, but it's also kind of the same thing we're doing over here. So this is also, we've got things that are sort of flipped to opposite sides of the minus sign. So you're trying to maximize this for Maxent and minimize this for AIC, but still, very similar things are going on here. You've got a term that rewards models that fit the data well, and a term that penalizes models that are complex. one thing here. Maxent gives you this, or rather the L1 lasso gives you this. It gives you this regularization multiplier that essentially controls how much you penalize the addition of new parameters to the model, right? So if you set this high, then it's going to be really reluctant to add a new lambda. And if you set this low, it's going to be happy to add new lambdas, or to increase the values of lambdas, I should say. AIC, in its term that penalizes number of parameters, the penalty per parameter is fixed at 2. And there is a mathematical derivation. There is a real reason why this is 2. It's not something someone just drew out of a hat. But it is set in stone. And here it's a user selectable, choosable hyperparameter that essentially tells you how badly do I want this model to be simple versus how badly do I want it to fit. And that's good to some extent that you have that control, but also you might want a more sort of objective external method for verifying whether your model is too complex or not. So Steph Seifert and I, she was an undergrad, I was a grad student at the time. We just set out to show whether we could use AIC or AICC to select regularization multipliers for Maxent models. So we're not replacing the regularization. So regularization, sorry, is this this phenomenon of restricting over parameterization. So we weren't replacing the regularization that's going on in Maxent. We were actually just saying, can we use AIC to select a value of that regularization multiplier that approximates the penalty for additional parameters that we would have if we were using AIC. Right, so we showed that if you use AIC to select the regularization multiplier for a Maxent model, we actually got better performance out of those Maxent models based on our simulated data for a bunch of different things that you typically want out of a model. So it did seem pretty promising, and people have certainly used AIC a lot from that. It's worth mentioning, though, that the simulations we did were fairly simplistic. There was no dispersal limitation, biotic interactions, and that sort of stuff. It's very simple. And so it might be worth revisiting this with a more sophisticated simulation framework. I would absolutely love to see somebody do that. It's also worth mentioning, as I sort of brought up already, there is a philosophical disconnect between machine learning and classical modeling and Maxent, even though the math is very similar between the L1 lasso and what AIC is doing here. Underlying that math is a fundamental difference in what you want a model to do. So it's worth just sort of keeping that in mind. And finally, a very practical issue. This is one that Jane Elith first sort of brought to my attention, but it's very true. Part of the justification for AIC penalizing, 2 times the number of parameters, whatever, is based on the assumption that there's this tight linkage between a number of parameters and a degree of freedom in a model. And with Maxent models, we're using the L1 lasso. That's not necessarily true. So because of the use of the lasso, the number of non-zero lambdas is not the degrees of freedom. There's a thing called the effective degrees of freedom in a Maxent model, which is often significantly less than it is when you're actually just sort of counting the number of parameters. And so, if anything, using AIC on Maxent models with the lasso is going to over-penalize the addition of parameters, right? So it's going to overestimate your degrees of freedom, and as a result, it's going to over-penalize the number of parameters. So, worth being aware of. If anything, AIC on Maxent models is going to be too strict. So, in general, just a summary, it seems to work okay. I feel pretty confident in that. Under the simulation conditions that we used, AIC seems to work better than just leaving Maxent's regularization multiplier at the default. But more robust simulations are possibly needed, and there's a couple of reasons why AIC is a weird fit. Yeah, I'm cautiously optimistic about it, but I would say the caution is as warranted as the optimism. So, Right. There's another way of selecting models that is completely different from what we've talked about so far. And I think vastly underutilized in niche modeling and distribution modeling, and that is visualization. I think we have done, as a field, and I'm including everybody in this, including me, an embarrassingly bad job of using the visualization tools that we have at our disposal. I think we should be visualizing everything. Not just making maps, but also looking at our models and thinking about them critically in environment space in terms of biological realism. So earlier I sort of blew past this, but you can build models for our simulated species that in geographic space make very similar predictions, but that in environment space look wildly different. So this is a random forest model, which just looks like absolute freaking nonsense to me as an estimate of some underlying biology. I can't even tell you a story about why this would make sense as an estimate of a species response to a set of environmental gradients. Whereas this domain model looks relatively straightforward, right? It's like, okay, it's probably, you know, glazing over some detail there. In particular, I doubt the fundamental niche is exactly rectangular. But at the same time, I trust this as a biological estimate vastly more than I would trust this. And this is not visible. These differences are not visible when you plot these models onto the distribution of environments on the landscape where this model was trained. It's just something you can only see when you visualize an environment space. And I'd like to think that most biologists, if they visualize these models this way and found that they have similar fits in geographic space, they would throw this one away immediately. I certainly would, and I hope you would as well. But the thing is, like, we're publishing models that look like this all the time. And the reason we're doing that is because we're not actually visualizing them. These plots are actually coming out of the new E&M Tools R package, by the way, if you're wondering how I did that. Yeah, check it out. It's very cool. Okay. I want to show you how bad this can get. Not to be depressing, but because it's important. I want to impress on you how essential it is to critically evaluate what your models look like in environment space. So this is a model for a real species. This is an anole from Cuba. Sorry, this isn't the best color ramp in geographic space here, but if you look closely, you can see this is purple down here, shading to orange and red. It actually does a pretty good job of saying where our species could be or versus where it isn't. We actually have a test AUC on this model of about 0.93, something like that. It's probably not well calibrated, obviously, but the discrimination accuracy on it is high. This is a GLM. It's based on 2 environmental layers. And when you plot this GLM in environment space, it looks like this. This is just like staring into the mouth of hell. This is chaos and nonsense. So think about what this is saying. These are those 2 environmental layers here. And again, bright colors represent the areas our model thinks are most suitable for our species. Dark colors represent the areas our model thinks are least suitable for our species. This model is saying our species hates most of the places it lives, which is existentially depressing. But it's also saying our species is just loving the most extreme habitat it finds. And in both directions, right? So it's liking the most extreme high value and the most extreme low value of this environmental gradient. So this model makes a great map, but as an estimate of biology, it is laughably wrong, right? And there's a reason this model is doing this. I just want to show this to you so you can have some idea. The reason this model is doing this is that these conditions are super common. So now this plot over here represents how frequently you see different combinations of environments across the landscape. And again, these are coming out of the new E&M tools. So this is basically saying these are really common environmental conditions in the landscape. And then this is the estimating of suitability of habitat. So what's going on here? Well, actually what's probably going on is this species does not give a crap about this environmental gradient. And so for the most part, its distribution is just reflecting the distribution of available habitat, right? An interesting thing happens here because we're building a model that tries to distinguish where we have seen our species from where we haven't. But if most of where we have seen our species is the same distribution in environment space as where we haven't, there's very little statistical signal that our model can pick out here, right? There's not a lot it can do to distinguish a distribution from itself. So what it's going to do is it's really going to focus on these combinations of environments that our species occurs in that we don't see a whole lot in our background data, right? And so it's going to pick the greatest outliers it can that it's found our species in. And so it's going to really upweight these points and really upweight these points, and that's how you get a model that looks like this. So again, this is a model that in geographic space gets a test AUC of 0.92, it actually is. In environment space, it is laughably wrong. Well, laughable if it wasn't so potentially problematic. But again, this is something you would not see. You would not know this behavior was here if you didn't actually visualize this model in environment space and think critically about what this model is saying is the underlying biology here. I'm not going to dive into these because this talk is already, I think, probably twice as long as they wanted. But I will point it out, in E&M tools, there's new metrics for actually measuring model fit in environment space. So you might actually say, hey, well, if you can plot models like this, why can't you measure model fit like this? And the answer is you can in the new E&M tools. And it's not just a two-dimensional space. You can measure model fit in an n-dimensional environment space for, we've got it set up for Maxent, Random Forest, Glim, GAM, PPM Lasso, BioClim Domain. I think that's it. Yeah, anyway, bunch of different modeling algorithms. You could do this sort of stuff. Yeah, so we have the ability now to, in the new E&M tools, to say you can measure model fit using all your favorite metrics in geographic space. You can also use those same discrimination metrics in environment space, which isn't perfect. It does seem to have some strengths. We've got a paper coming out about this soon, or that will be submitted about this soon, I'm sorry. We're submitting a paper about this soon. Measuring model fit in an environment space seems to have some significant advantages over doing it in geographic space for some applications. Yeah, but the tools are already implemented. You can already use this stuff, even though the paper isn't out yet. Right, so to summarize the big points here, model selection is a fundamental component of any modeling exercise. It is hard to overstate how important this is and how underappreciated it is in terms of the difference it makes to your conclusions. It's quite common to put a lot of thought into building models, like how do I curate my data points and how do I pick my study area, which algorithm to use, and which predictors to use. And we think about all these different things, and we put almost no thought, quite often, into how we're going to select our models and how that's related to our applications. And I think that's, I'm calling myself out here as much as anybody else. I think that's indefensible. I think we have to be really clear on what we're assuming our models mean and evaluate them appropriately. And this is really key, because I think to some extent we've given ourselves a pass on this idea that our model selection should be fit to purpose. We've given ourselves a pass because we've assumed that picking a model that's really good at one thing means we've got a model that's good at the other stuff too. And that is not the case. Like in the simulation studies we've got here, it is resoundingly not the case that picking a model that has a good AUC is going to result in a well-calibrated model and vice versa. So we need to be careful about that. So, big take home. Model selection must be fit to purpose. If you're going to set out to, estimate, for instance, the fundamental niche here, if that's a thing you could even do. You might want to, for instance, take an information criterion-based approach, which is really going to penalize overparameterization. So it's going to try to factor out these things that you're hoping are adding noise to your data and bias to your data. You're going to hope that there's a dominant signal of the fundamental niche, and that model selection will help cancel a lot of other stuff out. And yeah, whereas if you're wanting a model that just predicts where your species will be found next in a given more data collection like you've already done, you might want something that's just prediction focused. But it's worth noting, it's not just that a model doing this well is no guarantee that it'll do this well. It's that a model that does this well almost always cannot do that well because of how it's designed. So a model that predicts a species distribution well has to have these other things in it, whereas a model that predicts a species niche well has to have those out. Those are incompatible goals with most data sets, the only exception being where these three layers essentially don't change anything, right? In that case, you could do something that predicts the distribution and the niche well, but other than that, extremely unrealistic hypothetical scenario, you need to be clear on what you're building your models for, build them appropriately, and evaluate them appropriately. And this is why model selection, I wasn't kidding when I say I think this is one of the things that's the most important and one of the things that we do least well and have given the least attention to. This is fundamental. This is what tells you whether you've done a good job or a bad job. And so it's really worth putting a lot of thought into. And all right, with that, thank you very much. It's been really exciting to talk about this to you. I hope I wasn't too depressing. I find this, I tend to talk about it in all the ways it can go wrong, but it's also, like, I think about this as being one of the most exciting areas for development, because if we can get even a little better at selecting models for these purposes, we really can make better decisions and as a result make the world a better place. If anything, I hope that I've convinced some of you to explore model selection deeply and possibly do some cool simulation stuff or whatever to figure out what actually works for different applications. Because the truth of it is, we don't know right now how to do this best. And so 10 years from now, 20 years from now, we'll know a lot better, and it's because some of you out there will probably be doing the work to show us how to do it right. All right. Thank you very much, and yeah, talk to you later.